A neural network is a computational model inspired by the human brain, designed to process information through interconnected nodes. These nodes, or neurons, are organized into layers, with connections between them carrying weighted signals. Data flows through the network, from an input layer through optional hidden layers to an output layer, undergoing transformations at each step. Activation functions within the neurons determine how signals are processed and transmitted. Autoencoders, on the other hand, use unsupervised learning and consist of an encoder and decoder. The encoder compresses the input into a lower dimensional representation, and the decoder attempts to reconstruct the original input. A key difference is that standard networks predict a different output, while autoencoders aim to recreate the input itself. Consequently, standard networks are often used for classification and regression, whereas autoencoders are useful for dimensionality reduction, feature extraction, and anomaly detection. Essentially, standard networks focus on prediction, while autoencoders focus on learning efficient, compressed representations of data. Autoencoders possess a distinct architecture compared to standard neural networks, driven by their goal of learning compressed data representations. While standard networks often feature diverse architectures tailored to specific tasks like classification or regression, autoencoders adhere to an encoder-decoder structure. The encoder component of an autoencoder progressively reduces the dimensionality of the input, compressing it into a lower dimensional latent space representation. This compression is enforced by a bottleneck layer, a layer with fewer neurons than the input, forcing the network to learn the most salient features of the data. Standard networks, conversely, don't typically have this bottleneck constraint. Following the encoder, the decoder component attempts to reconstruct the original input from this compressed representation. This reconstruction process is the core of autoencoder training. The decoder effectively reverses the encoder's process, expanding the compressed representation back to the original input dimensionality. Standard neural networks, in contrast, have output layers designed for prediction, not reconstruction. The autoencoder's output layer mirrors the input, aiming for precise replication. This architectural difference reflects the fundamental distinction. Standard networks predict, autoencoders represent. The encoder-decoder setup, coupled with the bottleneck, distinguishes autoencoders from the varied architectures of standard neural networks, enabling them to learn efficient and compressed data representations. This compressed representation can then be used for tasks like dimensionality reduction, denoising, or feature extraction, which are not the primary focus of standard neural networks. The symmetrical nature of many autoencoders, where the decoder mirrors the encoder, further emphasizes the focus on reconstruction. Ultimately, the autoencoder's architecture is specifically designed for representation learning, a characteristic that sets it apart from the task-specific architectures commonly found in standard neural networks. A variational autoencoder, VAE, is a type of neural network that generates new data by learning the underlying probability distribution of the training data. Unlike standard autoencoders that learn a fixed representation, VAEs learn a probability distribution in a lower dimensional latent space. This is achieved by having the encoder output parameters of a probability distribution, typically a Gaussian, instead of a single vector. The decoder then reconstructs the original data from samples drawn from this learned distribution. This probabilistic approach allows VAEs to generate new data by sampling points from the latent distribution and feeding them to the decoder. A key feature of VAEs is their continuous and smooth latent space, which allows for meaningful interpolation between data points. They utilize variational inference to approximate intractable probability distributions, and the reparameterization trick enables efficient training by allowing backpropagation through random sampling. VAEs find applications in image generation, data denoising, anomaly detection, and generating new molecules, making them a versatile tool for generative modeling.